Let's start. Can you see the page, dependability of repairable systems? Okay, let's first start with a few definitions. For instance, repair, what is it? It restores the specified state. So if it's defective, you bring it back to the repaired state, or you can say also it is from the state down to state up. Failure is the opposite. It's the transition from state up to state down. Maintenance is something different. Maintenance keeps up the specified state. So that means you do not go to a service station with your car only when it's broken down, but in most cases it's just because the service interval is reached or exceeded, and then some maintenance is performed, like exchanging some lubricants, exchanging some wear parts which are worn out, and in that way it keeps up the specified state. In an idealized way, you could say, okay, the system performance and the system reliability is as it was in a new element or in a new system, but in fact, of course, it is not. It will degrade in some way, but here in a mathematical way, we keep up the state. Okay. So when we have the modeling of repair, we can say the equivalent to reliability is the repair function, and so that is the probability that it is repaired over time. And for that, again, we can find a density function of repair. That means how repair function changes over time. That's the first derivative of that. And we have a repair rate. That means how fast a certain percentage of repair is reached. Yes? For instance, you have 100 tramways, and out of these you repair one. So it's you could in a day. So you could say the repair rate is 1% of all tramways are repaired per day. Okay, that would be your repair rate. Of course, you have also an absolute repair, which is just the numbers of tramways that are repaired. But the repair rate means it is always related to the number that exists. Also, we have a probability of repair, and again, that can be described by this exponential function. So in fact, you could say for repair, you can take just the same mathematical modeling like you take for failure. It's just, you could say it's just the other way around, yes? Not from up to down, but from down to up. And if the repair rate is constant, then again, this repair function says 1 minus e to the power of minus mu t, where mu is the repair rate. And in that way, also you can take an inverse value of the repair rate, and here you could say mean time to repair is just 1 minus mu, or mu is 1 So let's say mean time to repair would be 1,000 hours. Of course, that's something which is very bad. Maybe you need 1,000 hours for an airplane that has crashed completely or so. And that would mean we have a repair rate of 1 million fit or so, which is, or 1 million equivalent to fit, and that would mean the repair rate is, yes, the repair rate is not so good. Okay, in that way also we can calculate that expectance value just by integrating the repair function from 0 to infinity, and again that gives us the mean time to repair. In a similar way we get the mean time to failure. Okay, what is availability? I would like to go through this here. Availability is the probability that a system is in the specified state at time t, and what is important, it is a repairable system. That is important. So you could say it is something like the equivalent to the reliability of a non-repairable system. The correct term here is availability if it's repairable. The complementary property is unavailability. That is again 1 minus the availability, which is called with V of t. And what we can do is we can derive the availability of a system in the case where we have data on the reliability of the individual components and information on the repair time. So generally we can say the mean time to failure is the integral of the reliability function over time, and the mean time to repair is the integral over the repair function over time. So one is, in the case of an exponential distribution, you can say that is described by the lambda e, that is described by the mu e, and in the end you want to have something like availability of the system. How available is it? So typically when we operate a system over time t, we want to know how many failures do we have in that time. Yeah? So you could say it in that way. You have your time pass, you have up, then you have repair, then you have up, then you have repair. And if you take the complete time and divide it by the mean time to failure, and also assuming, of course, that the mean time to repair is short, you get the number of failures for each element, E. And yeah, so here we could say E, and that's MTTF E. The time is, of course, same for all. The time of repair for the element E is just the number of failures times the time to repair. And so you can say the time to repair for each element is MTTR, E times T divided by MTTF-E, and in that way we can have that for each individual element. So the total number of failures up to time t is just the sum of all failures. And so you could say the total number of failures is just sum over all t divided MTTF E. And when we combine that, we can say the system's mean time to repair is the system's total time to repair divided by the total number of failures. And the system's total number to repair is T times MTTR divided by MTTF, sum over this divided by sum over 1 divided by MTTF. And in that way, we can compute the system's mean time to repair. So in that way, we can see a system is going up, it's going down, up, down. On the other hand, we can also assign not only a 1 and a 0, but we can also assign certain values. In that case, the performance of a system would be measured. But typically in our lecture, we will not use, let's say, individual performances. That's a different type of analysis, and we will not address this. But the average availability is now the mean time to failure of the system divided by mean time to failure of the system plus mean time to repair of the system. And in that way, we can again compute the individual, we can compute the availability over time, and in that case, we assume that we have an equilibrium of repair and failures, or failures and repair, and that means the availability of a system will typically be high initially, and it will go down and will go to this average availability after a certain time, while initially, of course, it was 100%. So, okay, so we have failures, we have repairs, and after some time, we have an equilibrium. And if we have such a system, that means roughly 10 repairs or failures. That's a rule of thumb. Then this average availability has been reached, and in that way, the availability of a system which is kept up is an average. So assume we have the tramway system here in Freiburg. We have a certain number of tramways. So we could say one tramway will fail every week. On the other hand, we can repair a tramway within a day. That means we will have a very high availability. Probably that would be 85% or so. And that means in that way we can compute what the average availability is. It is important, for instance, if we have an availability of 85%, then we must have either shorter repair times or we must plan with more tramways. So in case we have an excess of tramways, and in that way we can always be sure that all tramways which are necessary are available. Unfortunately, evidently, that is not the way how our traffic or our public traffic system is planned here in Freiburg, because there are very often breakdowns, especially in the Breisgau S-Bahn. And maybe if the planners would just keep in mind such simple considerations like computing availability and influences on it, then we could have a better service and a better availability. Okay. Now we can say, how can we model this? Because now it is a time dependency where the system is no longer linear insofar as after a certain time we can have a either or decision. For instance, if we have a failure, then we can have two cases. Either it is repaired or not. Yeah? We can have probabilities of repair, or we can have rates of repair. Yes, if you take probabilities, you could say, will it be repaired at all? If you have rates of repair, you can ask, will it be repaired within a day, or the repair time as an average value is 1 day or such a thing. Okay, so we have a system. That system can, for instance, be built up like this. We have two elements. It doesn't matter here presently if it's if these elements are in a series or parallel. You could say we have element 1 and element 2, and now we have again in space state 4 possibilities. All are functional. One is failed. The other is failed, or both are failed. Okay, again, we have 4 different states. Here you could say when is it functional, the system? In that case, only when case 1 is to be applied. In the case of redundancy, of course, you could say only in the state 4 the system would be failed. Okay. And now let's have a look at a model, and there was a graphical representation which is the Markov graph. And the Markov graph is a graph which now shows us, let's say we have only 2 states. It's a very simple system. It only consists of 1 element. And the state 1 is it is up, and state 2 it is down. And when we have a transition probability from state 1 to state 2, which is P12. That's a transition probability, and that in that case it's for failure, and that's for repair. So when it's failed, we have a transition probability to go back here. And of course, when we look at the system, we must say we have the individual probabilities of state 1, state 2. It's Z because in German Zustand 1, Zustand 2. The sum of all states or of all probabilities of all states, of course, is 1. So with 100% chance we are in any state. So in that way, we can model it. And on the other hand, we have the probability to be in state 1, we have the probability to be in state 2, and we have the transition probabilities to go from state 1 to 2. So that's a probability of failure. For instance, you could say it's 63% after the MTDF. And we have a probability of failure. And the transition probability with which the system stays as it is 1 minus P12 or 1 minus P21. Okay, in that way we can model it. So you could say, imagine we start here with 100%. Yeah? Then we have a failure probability, let's say, of 10%. Just make that example. So we have here 100% start. Yeah? Here that would be a 10%. What is the probability to be here? Again, that is 10%. So after that transition, we are with 10%. So now we have a probability of repair, let's say 50-50. So we go here. When we have a probability of 10% here we are with 90%, but then we repair here the 10% with 50%, so we are here in a 95%. And in that way, going around here, we can just compute the probabilities in which the system will be after each individual step. So that is T0, that is T1, that is also T1, and then that is T2. And in that way, we can model it. And if we have a system of more states, we can say the probability vector is the matrix of all transition probabilities. Here, in fact, it's a transposed matrix multiplied with the state vector of the initial state. So when you just begin, again, you are in a 1, 0, 0. You have the transition matrix and you get up that, and then in the next step you repeat it and you repeat it, and in that way you can compute the probability P1 to Pm as a function of time. Yeah? And in that way, you can say that is a possibility just to compute from the previous state to the next state, but what you must have is transition probabilities. And question is, where do we get transition probabilities? Of course, that's relatively easy. We get these from the failure functions or the repair functions of the individual elements. And in that way, we can say we know these data because we know the reliability of the elements, and in that way we can compute it. Doing it that way is a so-called Markov chain. So that is done stepwise, and these PII to PMM will constitute the matrix of transition probabilities. It is important to know when a system cannot transit from state I to state J, then by definition Pij is 0. When a system cannot come out from a certain state, so you are in state E and you have m different possibilities to come to state J. But if it cannot happen, then it's a so-called absorbing state. That means a system cannot come out of that state anymore. To say it a little blunt, if you are dead, you are in the ultimate absorbing state. Yeah, you cannot, after you are dead, you cannot come out of that state. And that's the same with the system. It's an absorbing state. In that system, in that state, the system is stuck. For instance, imagine you have let's say, a computer system and you mainly have faults. That means from a fault, the system can recover. It can reboot, for instance. But on the other hand, you would have, and now you only address software, and now you have a hardware failure. That would lead to an absorbing state, yes, because by hardware, you cannot come out of that state anymore, by software, for instance. And in that way, it is important to know these transitions here. The point availability is the sum of probabilities of all functional states. So that means if you have very many states of a system and you sum up all probabilities where a system is up, then that means ZJ is an element of the set of up states. Then you sum up all of these states, and that's availability. It's the same like system reliability. System is reliable, or the reliability is determined by summing up all probabilities of all states where the system is up. And it's the same with availability. You can say it's the sum of all probabilities where the system is up. Also, we must say when we look here, especially in new systems, the PA of T is higher than PAS after a certain time of operation. Okay, in that way, we have made some definitions. And on the other hand, we can have Markov states, and Markov states means always we have a certain time and we look at the next time step. And for instance, we have a repairable system that consists of two elements E1 and E2, and these are warm redundant elements. What does that mean for us? Warm redundancy means lambda 1 is larger than lambda 2. Yeah, so that's a primary, for instance, and that's a redundant. Element, and so that means the primary is in operation, so it has a higher failure rate. And now we can say we generally have 4 states, but in our case we only reduce it to 3 states. Here we can say element 1 and element 2 are functioning. So the probability is R1, R2. Then element 1 or element 2 has failed. In that case, we have to add these 2 states. So 1 has failed and 2 is functioning, plus the probability 2 has failed and 1 is functioning. So in fact, that's 2 states summed up in 1. And we have the third state, no element is functional. So F1 times F2 is multiplied. These are the probabilities we have here in our system. Again, we can say we have the failure rate of the active elements, we have the failure rate of the warm redundant elements, and we have a repair rate. Okay, so here we could say it's lambda and it's lambda of the redundant element. Okay, and now what happens? We can go from state 1, where all is functioning, to the state 2, where 2 have failed. And the probability in a short step of time is the failure rate of the primary, or also the other can fail, so we sum up both failure rates, dt. That's the probability to change over to state 2. We will not have a direct transition to state 3. All have failed. That could happen. That could be modeled, but in our case not. So, because we say it just fails by chance, not by a common cause or so. And in that way, we say, okay, first one fails, and then by another chance, the second fails. So we have the transition, lambda plus lambda r dt, and we come to state 2, where 1 is failed. So no fail, 1 failed, both failed. So again, here we must say the active or the redundant can fail, so we sum up the failure rates. When we are here in the state 2, we can have a failure of the last element, and that's always active, so it's lambda dt. And we go to Z3, all have failed. When we go from Z3, we say we repair back. We have a repair rate mu dt, and we go to Z2. But when we address here, we only address going away and 1 minus the going away. We do not add what is coming in. So we could say here we have probability to stay here is 1 minus lambda plus lambda r dt. The probability to stay here is 1 minus, so we go away with lambda dt and we go away with mu dt. So either the second fail or the first one is repaired. And in that way, here we know the 1 minus lambda plus mu dt. And when we are in Z3, we cannot come to another state, we can only repair. And so we have mu dt, and the probability to stay is 1 minus mu dt. Please keep in mind it's not 1 minus mu dt, but it is 1 minus mu dt, because that mu dt is a very small probability, of course. And so these transitions are computed using the matrix for time step to time step, and the time step must be very small compared to the mean times of failure. And in that way, we can compute how the system states change. And my proposal is that we do in the next week in an exercise. And in the end, what we can compute is the following. It is something like we have the P1, P2, P3. And so we could say, okay, the P1, at the probability of state 1, it will go down a little. The other probability can maybe go up, and still another probability can also go up, for instance. And that means, so that is Z1. After some time, we have a certain availability. We have Z2, and we have Z3. And when we add up Z2 and Z1, we have, for instance, the availability of our system. And in that way, we compute the behavior of the system over time, but we do it by a stepwise calculation, doing it for incremental time steps here. And of course, that can only reasonably be done with a computer. Okay, but we will see this in Excel in the next week. Okay, for today, thanks for your attention. And I would expect that the tasks I have given you are you try with it, and also you try to reproduce what I was showing you today. Okay?